has two parts. I can do one part. It's the same thing. Given that equation, it says find dy dt. Notice the derivative with respect to what? dt. See in the bottom dt? Given that x equals 5, y equals 12, and dx dt is equal to 6. So I'm going to take the derivative again. Notice with respect to t, it says dt. See in the bottom here? So the derivative of x squared is what? 2x times dx dt. Taking with respect to dt. The derivative of y squared, 2y times dy dt equals the derivative of any constant, which is what? 0. Plug in the values now and solve it for dy dt. X is 5, that'll be 2 times 5 times dx dt, which is what? 6, plus 2 times y, y is 12, times dy dt. 2 times 12 is what? 24. dy dt equals, what's 2 times 5? 10 times 6? 60. When you drag it to the other side, it becomes a negative 60. Can we get dy dt? Negative 60 over 24. You divide by 4, that's what? Negative 15. You divide it by 4, that's 6, is it? Is that negative 2.5? Yep, negative 2.5. So that's number 2. As part B, the same thing, different values. So once you get this derivative, just plug in the numbers and solve for whatever you need to solve for. Can't visualize it. What is that? A swimming pool, 12 meters long. Okay. That picture for me is horrible. I gotta make my own. So number 7. A swimming pool is 12 meters long, 6 meters wide, 1 meter deep at the shallow, and 3 meters deep at the deep end. Okay, this is what the pool looks like. I don't know. So this is from the top looking. It's 12 meters long, 6 meters wide. Here's the problem is, the bottom is not even. It's going like this, on an angle. I don't know, I can't really draw it, but 3D, I can't see it, but you're going like on, you're walking uphill with it. So when you look at the bottom, it's like you have a triangle on the bottom, because if you look at the bottom from the side here, if you just take a view from the side, this is what the bottom looks like. This is 1. This is 3. That's what the bottom looks like. This is 1 and this is 2. So when you're pouring water in it, it looks like a triangle there. I just can't I can visualize in my head, but I can't draw it on paper. I can see it there. I go, okay, this is what we got. So the question here is what? Water is being pumped into the pool at the rate of 19 cubic meter. Cubic, that's a volume. dV dt. 1/9 cubic meter per minute. Per minute. Being added, that's a plus. And there is 1 meter of water in the deep end. So the water right now is like this high. So the height is 1 meter. The first question, what percent of the pool is filled with water? Nothing to do with derivative. What percent? If we look at this section, just to find the volume of that, this piece here, the top half, the volume of the pool is, the top half is what? It's a, what kind of a shape we have there? Rectangular shape, right? The top half. So it's length times width times height. What about the bottom part?
It's a triangle.
It's triangle, okay. What's the volume of a triangle? Well, that's the area, 1/2 base times height, right? So the area, I'll give you a little hint. Volume of any shape is the area times the height.
Oh, so the sides squared 1/2 times the width.
If you look at it from this side, this is going to be the base, this is going to be the height, right? But it's deep. How deep is it in that direction? Isn't that 6 feet deep?
Yeah.
If that picture was taken from this, so that would be 6 feet, the depth of it, times the area of this piece, which is base times height. What's my base? 12. What's my height? No, for this piece. 2 divided by what? 2. Base times height divided by 2. Now the top part, we know that's going to be 12 times 6 times 1 plus that piece. So the volume of the pool, if we do that, 12 times 6 is what? 60, that's 72. 6 times 12 is what? 72 again? To fill that pool with water, you're going to need 144 cubic meters of water. Let's see how much water is in it now. The water in it is that little piece. We know this is 1. What's the base now? How do we figure out that length there?
Be half the original base.
Why half the original base?
Because it's half
You're
the
right.
original height. It's similar triangles.
That's what I was looking for. Similar triangles. Notice this triangle right there. and this big triangle. If you do the ratio of similar triangle, you get 12 here, and you get 2 down here. This one you got 1, and what is this value? Similar triangles. X will have to be 6. So when this is 1 foot high, this is actually 6 feet. The ratio of this side to this, 12 to 2, which is 6, should be the ratio of this side to this side. So how much water in it? Let's see the volume of the water. Again, that's a rectangular shape, the area times the height, or the depth of it. Well, the area is base times height divided by 2. And how deep this pool? 6 feet into. Just again, you take it, you're looking at it from this angle, but you have to picture it 6 feet deep. So what do we have? Is that 18? Cubic meters. So what percent of the pool is filled? The percent of water? It's 18 over 144 times 100%. We can divide by 2 because I'm sure they don't want decimal value. That's 9 over what? 9 over 72. Nine and 72. Can you divide 72 by 9? 8, right? So that's actually 100 over 8. 12.5%. So 12.5%. The next question is, okay, when you're at that height and you're adding water to it at that rate, how high or how fast the height is changing? So find dH dt when you're at that level. So the volume of the water right now, when you're at that level, at any given time, the volume of the water when you're at that level, how much water in it? It is the base. I'm going to use it as a function of x, not as a number. This is when it's 1, but I want it as a function of x. This is x times the height, which is h, because we're talking about this level here, at any given point during that time. So the base is x, the height is h. So x times h divided by 2, that's the area of this triangle. And how deep is it? 6. So the volume is actually 3 times x times h. Well, we got too many unknowns. The question, find dH dt. I got x here, so if I take the derivative, I have to use the product rule, I will have dx dt. But I don't know anything about dx dt. All I know, they want it when x equals to 6, when h equals to 1, when dv dt equals 1/9. There's no mention of dx dt. Can I rewrite x in terms of h? The answer is yes. Again, going back to similar triangles. This is 12. This is 2 for the big triangle. So we do a similar triangle. The ratio of x to h is the same as 12 to 2. X to h equals what? 6. X equals 6 times h. 6 times the height. So if I take this equation now, replace x with 6h, what do we have? The volume is 18h squared. Now take the derivative with respect to time, not with respect to h, not with respect to v, with respect to time. Derivative of v is dv dt. 18 times 2 is what? 36 times h times dh dt. Now plug in your numbers. dv dt is what? 1/9. 36 times h. What's h equal to? 1 times dh dt. Can we figure out what dh dt is? What's 9 times 36? 1/324 meters per minute. It's going to take a long time to fill that pool with water. The height is rising at the rate of 1/324. You will need 324 minutes to raise it by 1 meter. And actually, as you go higher and higher, the pool gets bigger. The rate slows down.
You were given dv/dt, right?
Yes, it says water was being added in at the rate of 1/9. And I know that's dV because it's cubic meters per minute. Cube is always a volume. It's tough to visualize that pool, but you have to look at 3D picture of it. This is you looking from this side of it, and remember it's deep. It's going into that yard for 6 more feet there, or 6 more meters. I don't know if these were feet or meters. Were they meters, I think? Yeah. We got another shape, and this similar to the pool actually, this one. We have this shape. I attempt to graph it, can't guarantee I will. God help me. I can't.
You said can. Can doesn't exist.
Something like this water is being poured in this shape. Doesn't look like their picture. The picture is nicer actually. But yeah, it looks like, from the front it looks like you have this triangle. That's what you have. And water is being added to it. And this is the height of the water, like. That's not bad actually. We know the water is being added here at the rate. This is, by the way, number 8. It says cubic feet per minute. Cubic feet, that tells you the volume. 2 cubic feet per minute. This, whatever the shape is 12 feet here, is 3 feet here, and the height from here to there is 3 feet. The water depth right now is h. That's how high the water is. The question, find dH dt, dH, not HH, when H equals 1.1 foot deep here. The key, the toughest part is really finding out what the equation is that ties all these pieces together, volume and height and all the good stuff. Again, you have to remember the volume, it's always area times height or length, whatever you want to call it. So when you're looking at that shape, if I'm looking at it from the front, what I see is that little triangle. Looks like this. That's what I see, the water. Well, what is the area of this water here? Isn't that 1/2 base times height? Times the length of it, how deep into in the back there that pool is. Whatever that shape is, probably not a pool. Trout there. What about that, the length of it, how deep is it? Isn't that 12 feet deep? It says you're 12 feet going in that direction. So the equation that describes that, 6b times h. This is the base, and this is the height. And just like the previous one, I can't have b and h in it. There's nothing mentioned about db dt, just the height. So somehow I have to get rid of that letter b. And to get rid of that, we do similar triangle again. Notice this is the big triangle. This is 3. And what's this side here? From here to there? 1.5, half of the whole thing. So the ratio, that'll be the same as b to h. So the ratio of this base, which is 1.5, to the height, which is 3, it should be the same as the ratio of this base to the height. What is b equal to? 2b equals what? h? b equals what? 1/2 h? So I know the base now is half the height. Go to this equation, see this one? And replace b with 1/2 h. What's the equation for the volume now? 3h squared. The question again, find, so I can get rid of that piece of paper, dH dt when h equals 1.1 and dV dt equals what? 2. Once you have this equation, it's not that bad. Getting that equation is the tough part. Take the derivative with respect to t. The derivative of v is what? dv dt. 3 times 2, which is what? 6h times dh dt. And now straightforward. There's actually two parts to this question. In this part, they ask you for dh dt, and they give you these values. In part B, they give you dh dt and h and ask you for dv dt. Once you get this equation, they're going to give you to find the third one. So it doesn't make a difference. So we'll just answer this one. I'm looking for dh dt. I know dv dt is 2. I know h is 1.1. What's dh dt? 2 over 6.6. 1 over 3.3. That was feet per minute, I think, the units.
Yes.
Yep. But once I come up with that equation, now I just plug in numbers. In part B, as I said, they're giving you dh dt, they're giving you h and asking for dv dt. They can give you this and that and tell you what, find the height. But they have to give you two of them, find the third one. And what's the last one? Oh. Is that 9? Yep. Number 9. Well, that's the last one. Construction worker. You have two pieces of wood, looks like this. Another one top of it. And a construction worker is trying to pull that piece of wood up there. The piece of wood, that's the piece of wood. It's 5 meters long. He's attaching it to a rope here, and he's pulling upward with it. It's moving upward. So the person is right here. He's holding that, pulling up on it. We'll make it she. She's pulling up on it. Yep. A construction worker, okay, pulls a 5 meter plank up the side of a building under construction, okay, by a rope and everything. Good, good. Assume that the opposite side of the plank follows a perpendicular to the wall. When I say wall, we're talking about this wall. So this is going straight up. It's not going on an angle, straight up. We're making that assumption, 90 degrees, which means Pythagorean theorem probably here. And the worker pulls the rope at the rate of 0.2 meters per second. So this here we'll call y, going in that direction. dy dt in the y direction, it's moving up at the rate of 0.2 meters per second. How fast is this end of the plank sliding along the ground? So we're looking for how fast is moving in this direction. We'll call it x. What's dx dt? It better be negative, by the way. Why? Because what happens to that distance? Decreasing. So that's what we're looking for. But when? When they want it when x equals 1.4. So this is x and this is y. We need an equation that will tie x and y together. What are you thinking? Can we tie x and y together? Is there an equation I can put them together? I know it's late, but think about it. Look at it. What do you see? Pythagorean theorem, a triangle. We have that equation. Now take the derivative. What's the derivative of x squared? 2x times dx dt. What's the derivative of y squared? 2y dy dt, all these with respect to time. And what's the derivative of 5 squared? Derivative 25 is 0. That's a number, that's a constant. Plug in the numbers, and you're good to go. 2 times x, what's x equal to? 1.4. I'm looking for dx dt, plus 2 times y, times dy dt, which is what? 0.2. So the only thing keeping me from solving the problem is what's y? Can we get what y is? Pythagorean's theorem. This is 5. This is 1.4. Can we get what y is? 5 squared equals what? Y squared plus 1.4 squared. What is 5 squared minus 1.4 squared? 23.04. Take the square root of that number. 4.8. On the money. I was wondering if I have to round anything. So now you put it in. And how many unknowns we have? Only one. 2.8 dx dt equals, when you take that to that side, 1.92 negative. What's dx dt? Negative 0.686. Round your answer to 2 decimal places, says in the problem. Negative 0.69. So the bottom is decreasing at the rate of negative 0.69 meter per second.